All right, so for this week in our support class, we're getting ready for some material that's going to come up in Chapter 9 in the parent class. Chapter 9 is all about trig identities. We've discussed many identities so far in that course, a lot of the standard ones, the Pythagorean identity, cofunction identities, even and odd identities, lots of that kind of stuff. But what we're going to be focusing on primarily in Chapter 9 is how to be given a trigonometric expression and then use the identities that you know to simplify it into a more manageable form, basically. And there's a lot of algebra that underlies the work that we do there. And so for today, our focus is on a purely algebraic concept, factoring quadratics and what we call factoring completely. So if you recall, in algebra, you talk about multiplying expressions of this form, x minus 1 times 3x plus 5, something like that. If you were to multiply this out using the FOIL technique that's usually taught in algebra, you're going to get 3x squared, and then you're going to get plus 5x minus 3x, because you're going to get 2x terms from that process. That comes out to plus 2x when you combine those like terms. And then negative 1 times positive 5, you'll get minus 5. Okay, so this is a quadratic expression. It's a polynomial with a degree of 2. And this side over here is factored. This side over here is not factored, even though these two expressions are equal to each other. They represent the same thing. One appears in a different form than the other. And in algebra, you show through a number of different techniques why it's useful to have a polynomial or quadratic in particular in factored form. The tricky thing is being given something that's not factored and factoring it, which means putting it in this form. So what we're basically going to do today is run through several examples of how to go about factoring polynomials, or quadratics in particular. So we're going to start with a fairly straightforward case. I want to factor x squared minus 12x plus 35. Okay. Notice I didn't write factor this, but that's going to be the instructions for everything we do. We're just factoring everything. Okay. Now, not every quadratic can be factored, but in this case, we can attempt to factor something using this technique that's usually called the diamond method. And for the sake of time, I'm not going to launch into a big long lecture on why this diamond method works the way that it does. We're just going to do it and then give an answer. So the way the diamond method works is if you have a quadratic of this form, x squared minus 12x plus 35, you take your constant term, which is 35, and you put it up at the top little sector of this big x shape here. Then you take the coefficient on your x term, which is a negative 12, and we put that down there. And here's your goal. We're going to fill in these two sectors here and here with numbers that do two things at the same time. The two numbers need to multiply together to make 35, and they also need to add together to make negative 12. If no two numbers exist, then you can't factor this. But if you can find a pair of numbers that satisfy those conditions, you use them to factor this. So let's think about this for a moment. Two numbers are multiplying together to make a positive number. The only way that can happen is if both numbers are positive or if both numbers are negative. In either of those cases, their product will be a positive number. But if the two numbers are also supposed to add together to become a negative 12, then that rules out the possibility that both of these numbers are positive, because a positive plus a positive will be a positive. So right away, we can deduce that both numbers are negative numbers. Okay, now think through different numbers that multiply together to make 35. So 1 times 35 is 35. Knowing that they should both be negative, though, that would be negative 1 times negative 35. So even though negative 1 and negative 35 multiply to the correct number, they don't add up to negative 12. What else multiplies to make 35? Well, again, they should both be negative, but negative 5 and negative 7 both multiply to make 35. And if you notice, they also add up to negative 12. So these two numbers hit both conditions. How do we use those numbers? Well, again, remember, we're trying to factor this expression, which means it should come out looking something like this. And we need to fill in the blanks, basically. These numbers fill in the blanks. -5, -7. This is the factored form of this. If you want to check your work to see if you got the correct answer, you can work backwards. Multiply this out and verify that you do in fact get this polynomial. I'll let you do that. Okay, now these ones are kind of the easiest cases, and what I mean by that is that the leading coefficient, meaning the coefficient on your x squared term, is a 1. You don't see a 1 there, but there is a 1 there that we could put, The trickier cases are the ones in which the leading coefficient is not a 1, but some other positive or negative number. So let's consider an example here. Let's see, which example did I want to do? I'm going to do, I have some examples pulled up in front of me. I just need to pick one. Let's do this one. I want to factor 2x squared minus 3x minus 9. Okay, so if I'm going to factor this expression, first of all, notice that my leading coefficient is a 2. It's not a 1. I can still use the diamond method for this technique, but you actually need to go about it a slightly different way. So some textbooks call this method the AC method. You may have learned it that way. The idea is to not just take my constant term and put it here like we did in the previous example. So this will not be a -9. Instead, what we do is we take the leading coefficient and multiply it to that constant term, 2 times -9. That would be -18. Okay? Now that we've done that, the bottom sector is exactly the way that we did in the previous example. It's just the coefficient on the x term, -3. Okay? And now we proceed with the diamond method, at least at first, in the same way that we did in the previous example. We're still going to look for two numbers that multiply together to make -18, but also add together to make -3. And running through some examples, you'll eventually notice that, first of all, let me back this up a second. We're trying to multiply two numbers together to make something negative. That only happens if these two numbers have different signs. In other words, one of them needs to be negative while the other one needs to be positive. Secondly, we're going to add these two numbers together to get -3. However, if you add a positive to a negative, you usually think of that as a subtraction problem. If I said 10 plus -7, you're going to think of that as 10 minus 7. So it's really easier to think of this as finding two numbers that differ by 3. Okay? After a little bit of work, it's not too difficult to land on this, -6 and +3. You'll see that they multiply to -18, but they add up to -3. Now in this case, I don't just want to write x minus 6, x plus 3, because look at what would happen if I did that. X minus 6, x plus 3, plus because it's positive, right? If you multiply this out, you're going to get x squared plus 3x minus 6x, so that's -3x minus 18. That is not what I started with, okay? And well, I could have just gotten the very first term and verified that. The leading coefficient is 1. So it's not the same technique exactly. What we do here instead is we take the two numbers that we found and we create fractions out of those. The denominators of these fractions are going to be whatever my leading coefficient in this polynomial was, 2. Okay? Same denominator for both. And then what I do is I simplify any fractions that can be simplified. 3/2, even though it's an improper fraction, which is totally fine, is already simplified. So I don't do anything with that one. -6/2 is not simplified. So I can simplify it to -3/1. Now normally you would just write -3, but I'm intentionally writing the 1 here because I need to use both my denominators and my numerators in both of these cases. The way that we factor this thing is we read these fractions from the bottom up. I make my denominators the coefficients on my x's. So this is 1x minus 3, or just x minus 3. This is 2x plus 3, because that 3 is positive. 2x plus 3. And I encourage you to go ahead and multiply these out to show that this is, in fact, the exact same thing as this. These two are equal to each other. Okay, so this is a beautiful technique. It's very easy to do once you've gotten a lot of practice with the diamond method. And it's faster than other approaches that are often taught for factoring these kinds of quadratics. Okay, let's go ahead and move on to some other examples. There's a very specific type of quadratic that occurs in practice, and it's called a difference of squares. Okay, so remember this term. The difference of squares is if I have something of the form a squared minus b squared. In algebra, you drill on this a lot. This always factors to the same form, a plus b times a minus b. Okay, and again, if you want to verify, multiply this side out and show that you get this left-hand side. But a quick example, how would I factor something like this? 100x squared minus 49. Well, again, you want to think of this as a squared and this as b squared. So a squared in this case is 100x squared. B squared is equal to 49. Okay? So if a squared is equal to 100x squared, then I could think of a as just 10x. Technically, a could also be negative 10x, but I'm going to go with the positive here. Notice if I were to square this whole thing, I would get back to this. If b squared is 49, then b, it makes sense, would be 7. So this gives me the a and the b that we're referring to up here. That means this factors to a plus b, or 10x, plus 7 times a minus b, or 10x minus 7. That would be the factored form for this guy. Okay, now I did this work down here, but in general, you're not going to ever see me do this work again because this is all easy enough to do mentally in most cases. Let me try a different example. I want to factor 27x squared minus 3. Okay, now this is going to be an example of something that I call factoring completely. And by factoring completely, what I mean is that there's usually more than one factoring step to take. So looking at this example, neither of these look like perfect squares. Looking up here, 100x squared is a perfect square, meaning I could take its square root and get something like this, 10x. But 27 is not a perfect square, and 3 is not a perfect square. However, both of these do have a common factor of 3. I know that I can factor a 3 out of both terms. In algebra, you call this factoring a GCF, or factoring a greatest common factor. So if I pull 3 out of both of those terms, then this becomes 9x squared minus, if I factor a 3 out of a 3, I'm left with a 1. 9x squared minus 1. Now the 3 is going to stay put, but if you look at what's in the parentheses here, this looks like a difference of 2 squares. 9 is a perfect square, it's equal to 3 squared. 1 is a perfect square, it's equal to 1 squared. So this can be factored down using my difference of squares technique. This becomes 3 times 3x plus 1 times 3x minus 1. And notice, by factoring completely, you oftentimes end up with more than just 2 factors in your result. I have 1, 2, 3 factors that are being multiplied together. Okay, so that would be my answer there. And this is where these can get a little bit more complicated because, again, you can factor GCFs out. Things can, you can kind of ramp up the difficulty with this. Let me take another example. 30x to the 5th plus 5x to the 4th minus 10x cubed. This one looks pretty bad. There's a few things that are indicating that. One, it's not a quadratic at all. It's a 5th degree polynomial. Remember, the degree of a polynomial is the highest exponent that shows up on your variable. But looking at all 3 terms, I do have a GCF, a common factor that can be pulled out of each of them. Notice my coefficients all are multiples of 5. 30 is 5 times 6, 10 is 5 times 2, 5 is 5 times 1. So I can factor a 5 out. But not only that, each of my variables here, x to the 5th, x to the 4th, x cubed, has a factor of x cubed that can be pulled out. So I'm going to factor out 5x cubed from the entire expression. Okay, now that I've done that, what I'm going to do is see what's left. So if I factored that out, I have 6x squared. And remember how this works. If you factor an x cubed out of an x to the 5th, for example, you subtract the exponents. The 5 here minus the 3 that I pulled out gives me a 2 here. Plus, this would be reduced to just an x, and this would become minus 2. Okay? Now, the 5x cubed is going to sit there just like the 3 did in the previous example up above. But this stuff in here, what's left in parentheses, is now just a regular quadratic. And that can be factored the way that we did in one of our previous examples. Notice my leading coefficient is not a 1. I'm going to use that diamond method, but I'm going to use the version where I multiply 6 times negative 2. So I have negative 12. And then the coefficient on my x term, even though it doesn't look like there's 1, is technically a 1. Okay? Which two numbers multiply to make negative 12 but add up to 1? Well, I could see that 4 and negative 3 would have done it. Okay? But remember, when you have that leading coefficient that's not equal to 1, like we do here, we use that as a denominator in both of those fractions. And in this case, both of these fractions can be simplified. That becomes negative 1/2. This becomes 2/3. And again, what we do is we read these fractions, these simplified fractions, from the bottom up by putting an x with our denominator. So this becomes 3x plus 2. Don't forget your 5x cubed is still out there. 3x plus 2. My second set of parentheses is 2x minus 1. And this is now factored completely. Okay? Notice again, it's the same idea as what we did before. You factor as much as possible. And if you wanted to, you could multiply all of this out. You should get back to this where you started from. Okay? Now there's lots of different examples that we could do. I want to do one more type of example, which is using something called substitution. So in this case, let's take a look at, let's see, this polynomial here. X to the 4th, where did it go? I have my example right in front of me. Here we go. Plus 2x squared minus 24. Okay? I want to factor this polynomial. Now the method that I used up here actually won't work anymore because I noticed something similar that I did up here. This is not a quadratic. If it were, its degree would be a 2, and it's not. So this being something that's not a quadratic is not going to factor in the same way. Up here, the technique that worked was to factor a common factor out, the GCF, which was 5x cubed, and then what was left over was a quadratic, and I could break that down further. But the GCF of these three terms is just 1. I can't pull anything more out of this. So that technique's not going to help me this time. So what do we do? Well, what we're going to do is something that's very common in calculus. It's called making a variable substitution. Here's something that I actually noticed, and you may not notice this on your own right away. But that very first term, x to the 4th power, can be written as x squared squared. That's using your power to a power property for exponents, which says that if you're raising a power to another power, you multiply those exponents together. Now, why did I do that? Well, now I'm seeing the expression x squared showing up in two different places, here and here. What I'm going to do is define a new variable. I'm going to say let u equal x squared. Okay? If u is equal to x squared, I can use this u as a substitution for anywhere I see an x squared in my expression. So this is going to become, instead of x squared squared, it's going to become u squared. And this becomes plus 2u. And then this minus 24 didn't have any x's in it, so there's no substitution necessary. And by doing that, even though I've introduced a new variable, the new expression is a quadratic expression in that variable, and that can be factored. So now let's create our diamond. This has a leading coefficient of 1, so all I need to do is take my constant term, negative 24, and my term on my coefficient on the u here, which is just 2, put that there, and now I'm looking for two numbers that multiply together to make negative 24, but add up to positive 2. It's negative, so one should be negative, the other should be positive, and without too much work, you should be able to see that negative 4 and 6 do the job. Okay, so with that, I know that this is going to factor to u minus 4 and u plus 6, okay? But you don't want to stop here, because the original problem was given in terms of x, not u. The u was just a temporary patch or a temporary fix to be able to get to this point. Now that we've gotten to this point, I can put the x squared back in for where the u's are. And this becomes x squared minus 4 and x squared plus 6, okay? And so at this point, you might look at this and think, okay, cool, I'm done. I've factored this, and my x's are back in the expression. I can call it a day. Except if you notice, one of these two factors is a difference of squares, this one in particular, x squared minus 4. 4 is a perfect square, x squared is a perfect square. And so that can be factored even further. X plus 2, x minus 2. Now this thing here is not a difference of squares. For one thing, 6 is not a perfect square, and for another thing, even if it were, that's a plus, not a minus. And you cannot factor sums of squares, only difference of squares. So this becomes x squared plus 6, and now we're done. Okay? So that's kind of a selection of different factoring problems that should be able to get you through the assignment for this week.